Hi, everyone. My name is Adi Foord. I'm an assistant professor at the University of Maryland, Baltimore County. I am also co-lead for the AXIS AGN Science Working Group, and my area of expertise is dual AGN. So today I'll be talking about how AXIS will really impact the field of dual AGN and allow us to better understand supermassive black hole growth during galaxy mergers. So galaxy mergers are believed by some to play an important role in the fueling and growth of the central supermassive black holes. And these are simulations of the time evolution of a collision of two spiral galaxies that each have their own central supermassive black hole. And it includes the effects of the supermassive black hole hosted at the center of each galaxy. It's thought that galaxy mergers can introduce periods of activity within the supermassive black hole's lifetime. And during these periods of activity, the large-scale energy input from the supermassive black holes, or feedback, can regulate the growth of the host galaxies. And so you're seeing some of that feedback in the simulation right now. And simulations like the one that I'm showing have showed that mergers are able to transport gas reservoirs to the inner regions of galaxies from which the supermassive black holes can begin accreting and trigger this nuclear activity. So simulations support the idea that mergers might play an important role in the fueling and growth of central supermassive black holes. However, observationally, trying to better understand if mergers trigger supermassive black hole growth a lot more than supermassive black holes might undergo outside of a merger environment is really, really hard to do. And the question that observers try to answer is, are AGN more likely to be found in mergers, or do you find a higher frequency of AGN in mergers versus isolated systems? And if you go through the literature and try to see what people have found, you'll see that there are conflicting results. So some studies find that AGN are more likely to be found in mergers, and some studies find that AGN are not more likely to be found in mergers. And there are various reasons that are thought to be responsible for these conflicting results. There's a lot of observational biases that can creep into your study. It depends on the redshift regime that you're focusing on. It depends on how you're defining an AGN, which diagnostic you're using, etc. So one avenue for gaining better insight on the connection between mergers and supermassive black hole growth is studying systems called dual AGN. And dual AGN are unique observational flags of merger-driven supermassive black hole growth. To quickly summarize what a dual AGN is, a dual supermassive black hole is a system that you find at the earliest phases of a galaxy merger, and I'm showing that here on the left-hand side. The two galaxies which are merging are still at kiloparsec scale separations, so the two central supermassive black holes don't know about one another. They're not gravitationally bound at this point, and this system is mostly losing energy, which is allowing the separation between the two galaxies to decrease due to dynamical friction. And so a dual supermassive black hole, where both of the black holes are actively accreting and are in an AGN state, is a dual AGN. So dual AGN represent a moment in time during a merger where both supermassive black holes are in a growing and active state, and thus studying their frequency and their environments can help us better understand any possible links between mergers and supermassive black hole growth. We believe that dual AGN are a result of galaxy mergers, and galaxy mergers are quite ubiquitous in our visible universe. We see them all the time with our large optical surveys. However, there are fewer than 50 confirmed dual AGN to date. So there's a very big discrepancy between the number of confirmed dual AGN and the number of known observed galaxy mergers. This figure is showing many dual AGN candidates that have been posted in the literature, and it's showing their physical projected separation as a function of redshift. These dual AGN candidates, dual AGN candidates have been found as early as 1985, and this is showing detections up to 2021. So it is a bit dated at this point in time, and there are a handful of new strong dual AGN candidates that are not on this figure. These dual AGN candidates have been detected using a wide variety of techniques. A lot of them are from optical spectroscopy. Some of them are direct detections using radio or X-ray observations, and others are from optical photometry. So the two main takeaways from this figure is that there are way fewer dual AGN, even candidates, known than galaxy mergers. And we haven't discovered very many dual AGN candidates at separations below a kiloparsec and at large redshifts. And the reason why that we aren't finding very many dual AGN in these two areas of parameter space is a result of us currently being constrained by both the resolving power and the sensitivity of our available telescopes. And I'll get into that a little bit more later. In addition to better understanding the role that mergers play in supermassive black hole growth, finding more high Z dual AGN will be important for modeling the expected gravitational wave signal. These are semi-recent results from Nanograv. They released in the spring of 2023 this suite of papers showing results from their 15 years of data collection. And in the rightmost panel in this figure, they are showing the redshift distribution of the mergers that they believe are contributing to the signal that they are detecting. And you can see that the redshift peaks at values below 1. So these are nominally nearby sources. In the panel directly to the left of this panel, you're seeing the redshift distribution of the progenitor supermassive black hole pairs, defined as having physical separations equal or less to about 10 kpc. And they represent the initial supermassive black hole pairs that eventually evolve into the mergers. So at separations of 10 kpc, we're dealing with dual supermassive black hole systems. It's still relatively large separations between the two nuclei. And we can see that the initial dual supermassive black hole population that's contributing to the PTA signal maybe peaks at redshifts between 1 to 3. So quantifying the frequency of dual AGN at these redshifts, and also as a function of redshift, will directly connect to the gravitational wave signals that the PTA team is believed to be sensitive to at lower Z. And it can help with their models and with their constraints if we have a better understanding of the population at high Z. So observationally, we don't currently know what the frequency of high Z dual AGN is or the evolution over cosmic time. In this figure, I'm showing the dual AGN fraction as a function of redshift, and this is pulled from our AXIS white paper series, which has actually now been published in Universe. So, so go check that out. In pink, I'm showing the statistical probability of detecting 2 X-ray AGN in a galaxy merger. So what this X-ray dual AGN fraction might be, assuming that the probability of finding an X-ray AGN is not affected by the merger environment. So this curve was derived by weighting the expected X-ray incidence of a single AGN by the observed galaxy merger fraction as a function of z. In purple and green, I'm showing results from cosmological simulations that include accretion physics that's introduced by galaxy mergers. And you can see that there's a slight difference between the expected magnitude of dual AGN and mergers that the simulations predict and that our analytical description of the dual AGN fraction predicts. And in general, if mergers play no role in enhancing supermassive black hole growth, the expected frequency of dual AGN might be below 2% at all redshifts. However, as I noted, these large-scale cosmological hydrodynamical simulations that do model the physics associated with supermassive black hole accretion during mergers predict that the frequency of dual AGN should be a factor of about 2 or so higher. Our current observational constraints on this dual AGN fraction are shown in brown. This most nearby constraint was carried out in COS 2012, and this high Z upper limit was just recently placed by one of my students, and our paper has just been published in AppJ, and I encourage you to check it out. It's called Searching for the Highest Z Dual AGN in the Deepest Chandra Surveys. And so this was one of the first times that we could place a high Z X-ray upper limit on the dual AGN fraction. So we want to add more data points to this plot, and we want to add data points that are much more constrained, so that aren't upper limits or that maybe have smaller error bars. And this will just give us a lot more insight on the role that mergers maybe play or don't on supermassive black hole growth, as well as the incidence of supermassive black hole mergers at redshift ranges that are important for the expected gravitational wave signal. All right, so now to talk a little bit more about AXIS and how AXIS is going to really help us out with our searches for dual AGN. What I'm showing on the left-hand side is a mock deep 5 megasecond stare with AXIS. And it has a large 24 arc minute radius field of view. There's 3 insets shown, one in green, one in yellow, and one in red. And these insets are representing what the data looks like at different off-axis angles. So in green, we have an off-axis angle of 0, in yellow, 4 arc minutes, and in red, 7 arc minutes. And we're comparing how this deep stare with AXIS looks versus what a deep stare with Chandra looks like at the same off-axis angles and at a similar depth. So you can see that for all of the off-axis angles, AXIS is observing many more point sources than Chandra. You can see that also because of AXIS's sensitivity, it's detecting emission associated with a cluster that was simulated at the center of the field of view, and Chandra isn't able to detect any emission associated with that, any of that diffuse emission that's associated with the central cluster. You can also see that as we move to larger and larger off-axis angles, the PSF of Chandra degrades quite quickly, so your point sources look more elongated, while the point spread function of AXIS remains relatively stable and things still look like point sources, even when you're pretty far out on the field of view. So those 3 things combined, the stability of the PSF, the really large field of view, and the sensitivity of AXIS is why it's such a powerful observatory for finding more dual AGN. And although the AXIS PSF is marginally larger than Chandra's on-axis PSF, which is what you're seeing in this figure, as you move off axis, you can see how Chandra's PSF exponentially increases once you get to an off-axis angle around 3 arc minutes or so. And AXIS's stays relatively stable as you move off axis. So Chandra's PSF is one of the largest constraints currently when we're trying to carry out blind searches for dual AGN. We are already working with a relatively small field of view, which is an 8 arc minute by 8 arc minute CCD. And then within that field of view, we're restricted to sources with off-axis angles below about 3 arc minutes or so. So it's a very small percentage of the total data that we can really use when we're trying to search for dual AGN. So the stable PSF of AXIS will be one part in helping discover over an order of magnitude more AGN pairs than we currently can with Chandra's surveys. So it's not only the stable PSF, but like I said, also the effective area or its sensitivity and its large field of view. These are simulations of a dual AGN as observed by both Chandra and AXIS. This dual AGN system has an X-ray luminosity of 5 × 10⁻43 ergs per second. It's sitting at a redshift of 3. The dual AGN simulation has a separation between the two AGN of about 1.5 arc seconds, which at a redshift of 3 is close to 12 kpc. And the count ratio between the secondary and the primary AGN is 0.5. So what that means is the secondary AGN has a luminosity that is about half as luminous as the primary. So this is a 300 kilosecond observation with both Chandra and AXIS. And we're also looking at how the observation varies as a function of the off-axis angle. So we have off-axis angles of 0, 3, 5, and 7.5 arc minutes. So on AXIS, Chandra observes only about 18 counts associated with the dual AGN, while AXIS observes about 150 counts associated with the dual AGN. And we're showing the size of the point spread function in this black dotted circle. So you can see that as we move off axis with Chandra, our PSF becomes huge at an off-axis angle of 7.5 arc minutes, while it remains relatively compact with the AXIS observations. So in general, given the PSF of AXIS, its effective area, and its large field of view, a single 300 kilosecond AXIS pointing should result in a sensitivity to detect about 20 times more dual AGN than we could with a similar Chandra ACIS-I pointing. To better understand the types of constraints that we can carry out with AXIS, we created a mock sample of AGN that were detected by AXIS, and we simulated a mock deep survey and a mock intermediate survey. And these mock surveys were carried out via end-to-end AXIS simulations with the 60 tool, and this was led by Stefano Marchesi. So the mock deep survey was a single stare that was 7 megaseconds, and the intermediate survey was 2.5 square degrees with 375 kiloseconds per pointing. So combining these two surveys, we selected AGN that met the following criteria. They have an X-ray luminosity greater than 10⁻42 ergs per second, and they have more than 50 counts between 0.5 to 8 keV, and they have off-axis angles under 10 arc minutes. And we imposed these cuts to form a sample of AGN where it would be very easy to see if it was a dual system. So for example, if you have less than 50 counts and you assume a standard flux ratio of about 0.1, the secondary is going to be contributing less than 5 counts. And that will be very hard by eye to claim that you have a dual AGN. And our luminosity and off-axis angle cuts follow a similar reasoning. So below 10⁻42 ergs per second, we might suffer from contamination from X-ray binaries and or ultraluminous X-ray sources. And at off-axis angles under 10 arc minutes, the average AXIS PSF half energy width remains at around 1.6 arc seconds. So after imposing these cuts, we have a sample of about 10,000 X-ray AGN that we want to then use to search for dual AGN. And just for fun, we compared the distributions in redshift space as well as in count space to a sample that we create using available Chandra survey data. So we used XUDS, AGIS XD, CDFS, and the Cosmos Legacy Survey. We imposed similar luminosity and count number cuts. We had an off-axis angle maximum of 4 arc minutes because of the Chandra PSF. And after these cuts, we only have 420 Chandra AGN that we can now use to look for dual AGN. So you can see that the Chandra surveys, not only is the number obviously much lower, but they don't span across as large of a redshift range as the AXIS mock sample allows us to investigate. And in general, we have way more counts associated with each AGN, which just gives us a much easier time searching for duals. All right, so taking this sample of mock AGN, which is around 10,000 AGN, and assuming that the expected dual AGN fraction should match what the cosmological simulations are predicting, we find that we can statistically, and these error bars are showing the 95% confidence limit, statistically discern between the predicted merger versus secular dominated dual AGN fractions across a redshift range of 0 up to about 4 or 5. So because our sample size is so large, our error bars will be pretty small, and it'll allow us to statistically differentiate between what the simulations predict and what our analytical description of the dual AGN fraction predicts. Interestingly, this nearby observational constraint, if we want to treat it as an anchor for what the true dual AGN fraction is, and perhaps it really is much higher than what the cosmological simulations are predicting, if we use this data point as an anchor and we take our black data points and kind of shift them up to meet that anchor, we might expect the X-ray dual AGN fraction to peak at values closer to 8%. At a redshift around 2. And so this would amount to detecting hundreds of more dual AGN than predicted by the cosmological simulations and really boost our population statistics. And just one small note here, both of the cosmological simulations that I'm showing on this figure, which are the Horizon and Astrid simulations, have been derived specifically for our AXIS data set. So in particular, each AGN pair has a bolometric luminosity greater than 10 to the 43 ergs per second. And all dual AGN that these simulations are sensitive to have separations greater than 1.5 arc seconds and less than 30 kpc. And we tweaked the dual AGN fraction so that it matched what we might expect to be sensitive to detect with AXIS. So once again, assuming that the dual AGN fraction follows predictions from cosmological simulations, we probabilistically assigned physical separations to each detected dual AGN, sampling from a distribution of physical separations that have been measured for nearby X-ray dual AGN. And in doing so, what I'm showing you on this figure is in purple data points what those probabilistically assigned projected separations are, the given redshift of each dual AGN, and how our dual AGN detections compare to the current Chandra detections, which you will see are mostly constrained to the nearby universe, as well as the sensitivity of future and or current observatories such as New Athena and Rosita. So you can see that AXIS's terrific point spread function allows us to be sensitive to these dual AGN systems that have separations less than 30 kpc. And so we won't be sensitive to those systems with Athena or New Athena or eRosita. And with respect to the current Chandra detections, we will be finding a lot of high redshift dual AGN. So it's really the best of both worlds. And again, this is just showing an example of what one of these mock dual AGN look like at a redshift of 3 in Chandra versus AXIS. So because we're getting so many more counts associated with each dual AGN, it'll be a lot easier to not only detect them, but better constrain their X-ray properties. All right, so our ability to detect dual AGN in a given AXIS observation can be amplified using available statistical tools. And so here I'm plugging one of the statistical tools that I have developed that is called Baymax, Bayesian Analysis of Multiple AGN in X-rays. And here is our fun mascot for the code. So very briefly, Baymax uses a Bayesian framework. It estimates the Bayes factor for a given X-ray observation, and it will tell you the likelihood that your observation is composed of a single versus a dual X-ray point source. And it can do this very well because it has very robust descriptions of the point spread function for whichever instrument that you are using. And it models the point spread function for each unique observation. So, including details like the time the observation was, the orientation of the telescope, the placement of the AGN on the CCD, etc. And so on the left-hand side, I'm showing results from Baymax when we run it on thousands of simulations of dual AGN that have been detected in Chandra. And these dual AGN simulations have had a range of count ratios, which is, again, the ratio of counts associated with the secondary versus the primary, and angular separation. So you can see that at the most extreme regions of parameter space, where you have a very large separation, 1 arc second, and the count ratio is high. So a count ratio of 1 means the secondary has just as many counts as the primary. You have very large Bayes factors. And as you move to smaller count ratios and smaller angular separations, your Bayes factor, or the strength of your evidence that you have a dual point source model, the strength of your evidence that the dual point source model is favored is lower. And in dark blue, we're showing regions in parameter space where we don't feel very confident that we could correctly detect that you have a dual AGN. So you can see that for a Chandra observation with about 200 counts, we can probe separations that are close to or even below 0.4 arc seconds, which is really cool. And this is a simulation of a single AGN as viewed by Chandra versus a dual AGN as viewed by Chandra, where the dual AGN has an angular separation below 0.5 arc seconds and a count ratio of about 0.62. They both have about 200 counts. And so you can see that by eye, it's just impossible to tell that this is a dual AGN. And that's why statistical tools like Baymax are really helpful. So Baymax did flag this simulation as likely being a dual point source system. And so just to take this angular separation and put it into a physical separation, if this source was at a redshift of 1, this would be a physical separation of about 3.5 kpc. And then, of course, it depends on the number of counts that your observation has. So the fewer counts you have, the less area and parameter space you can access. And the more counts you have, the smaller the separation you can push with Baymax. And so we haven't really been able to push to angular separations much below 0.3 arc seconds. But the more counts you have, the more powerful your statistics. So tools such as Baymax can push analyses on AXIS detections to dual AGN with separations near 0.6 arc seconds or so. So this is a similar grid as what I previously showed you, but specifically for hundreds of simulations of dual AGN as observed by AXIS with various count ratios and various separations. So you can see that at around 0.8 arc seconds, we have pretty good sensitivity across a really wide range of count ratios. And if you want to get to smaller angular separations like 0.6, you will be restricted to the largest count ratios. Of course, this will look different if you have 50 counts or if you have 700 counts. So although the AXIS simulations don't allow us to probe angular separations as low as Chandra observations, and that's really just driven by the size of the point spread function, we do have a similar sensitivity in parameter space around 0.8 arc seconds and higher, which represents about 6.5 kiloparsec at a redshift of 1. And at the lower separation limit, where Chandra is probing separations near 0.4 arc seconds, and AXIS is probing separations near 0.6 arc seconds, the physical separations are not significantly different in terms of the stage of the merger. So at Z of 1, this represents about 3 kpc, and at Z of 1, this represents about 4.8 kpc. So we're still probing a population that's very similar in merger stage with AXIS as we can do with Chandra. And this is showing a simulation of a single AGN as observed by AXIS and a dual AGN as observed by AXIS when you have an angular separation of 0.6 arc seconds and a count ratio of 0.3. So again, by eye, we wouldn't classify this as a dual AGN. And so statistical tools like Baymax will greatly expand the population size. And this is to show that once again, the power of AXIS lies in its extremely stable point spread function. So this grid, which is an on-axis sensitivity grid for AXIS observations, it looks very, very similar as you move to off-axis angles of, 3, 4, 5 arc minutes. And that's not the case for Chandra data. So this is your AXIS PSF 10 arc minutes off axis, and this circle is showing a 2 arc second radius. So at 10 arc minutes off axis, most of your point spread function is still within a 2 arc second radius. And this is showing the Chandra PSF at a 10 arc minute off axis angle. You can see that it's a lot larger than a 2 arc second radius circle. And this is the biggest reason why it's hard to find dual AGN. You have this extension, and so you lose sensitivity along an entire axis when you're searching for the probability of there being 2 point sources. So I've reached the end of my talk. I will quickly summarize. Although dual AGN are an expected process of galaxy mergers, the number of confirmed dual AGN remains much smaller than the number of known mergers. And AXIS's excellent PSF, the stability of the PSF, its field of view, and its sensitivity are all working together to greatly expand the known number of AGN pairs. And we can do this, we think, by over an order of magnitude, which is amazing. Quantifying and constraining the rate of AGN pairs as a function of redshift will act as a benchmark for future galaxy evolution simulations. So once we can actually start adding data points to the fraction of dual AGN as a function of redshift and comparing that to predictions from analytical constraints versus cosmological constraints will give us a lot of insight on how galaxy mergers are or are not contributing to supermassive black hole growth. And then lastly, analyzing high-resolution X-ray images with statistical tools, we do expect that we can find even more pairs of AGN in the AXIS fields. So thank you so much, and that's all I got.